Let's do a more serious example just to revisit some of the processes that we learned about, right? So what did we learn? We learned that there is an equator to pole temperature gradient that is set up because Earth is a sphere. More energy is being received at low latitudes than is being lost back to space, and higher latitudes are losing more energy to space than they are receiving. Okay, so the main thing, as it will turn out, that the equator to temperature pole gradient gets affected by global warming. So we have the whole weather and climate system trying to serve this energy transport, and one of the main player in this is the latitudinal moisture transport, right? So the moisture is being evaporated in warmer latitudes and being pumped into higher latitudes. It's complicated, as we saw, with the Hadley cell, Ferrel cell, polar cell, and so on. And when we get into, if you get into mathematical aspects of this meridional circulation, we will see that actually Ferrel cell is not really a cell. There is other ways that energy is moved across those latitudes and so on and so forth. So let's say you want to understand these feedbacks. Then you have low latitude warming is going to lead to high latitude warming eventually through various feedbacks like latitudinal moisture transport, which essentially means you're going to move more energy from low latitudes to high latitudes, and high latitude warming will in turn affect the low latitude warming by requiring less energy to be transported to the poles, for example. That's what is happening now. We will see the warming patterns in more details. At high latitudes, if you warm it, you're going to have less ice. Less ice means decreased albedo, right? Ocean is darker, land is darker. If you remove snow, land is darker. That's going to increase the amount of energy being trapped in the system because you are reflecting less solar radiation back. That's going to lead to atmospheric heating and more high latitude warming. So you have a loop there, but you have another loop. If less ice, then evaporation can increase. So if you reduce sea ice, which is a very good insulator, ocean is going to evaporate more because cold atmosphere, even though high latitudes can be warmer, the atmosphere is still pretty damn cold. So it's going to sweep up more water vapor from the ocean. So you can have more summer clouds. So even though Arctic is cold, cloud feedbacks there are very strong. Okay, this is not very intuitive. Then you can have a negative feedback because those clouds can be bright and increase the albedo. So that can affect the balance through this loop. They can also have a negative feedback and reduce the impact on net radiation, which is coming through earlier snow melt. Right? If you warm the higher latitudes, what's happening in the Arctic or over land is that snow falls, and then if it doesn't melt during the summer, more snow can fall on top. Or if the sea ice forms, if it doesn't melt through the summer, then it can reflect more, and more sea ice can form in the next season, right? Next winter. So that cycle can be altered as well when you have high latitude warming. Not just sea ice loss, but also snow melt can happen earlier, which can decrease the albedo. So you have these sea ice loop and the snow melt loop, and you can also have a vegetation included in there. If there is enough early snow melt, then biology responds quickly, and you have the typical shrublands, so-called tundra, growing pretty fast, which can also decrease the albedo because they are darker, which means they can trap more energy or reduce the outgoing, reduce the reflection of shortwave and increase the warming, right? So you have these kind of interwoven complicated feedbacks. Okay, so when you perturb one particular situation, you don't know how many other feedbacks are running through the system. One exciting example was that there was a loss of pollinators in a little forest near the shore of a water body. I don't remember if it was a lake. And to investigate why pollinators were disappearing, they started looking at the whole system. It turned out that the bees are eaten by dragonflies. Dragonflies lay their eggs in the water where the forest was. The dragonfly larvae were being eaten by fish in the water. The fishermen on the coast were catching the fish, and fewer larvae were being eaten because the fish were being removed. So more dragonflies were being bred and more bees were being eaten. So you can see how fishing affected the entire loop and the pollinators. Okay, so just an example. There are many such complicated unintended consequences that run through these complicated, interconnected, strongly coupled loops. We will see there are some loops that are strongly coupled, some loops that are weakly coupled, some are positively coupled, some are negatively coupled, and so on. So Earth's system is complicated even on its own, but human beings end up adding more complications to the whole system by perturbing it somewhere. So where you perturb it and when you perturb it can have a huge impacts of cascading further impacts down the network.